Okay, hello everyone to the class today. So as a first thing, let's just go through the challenge that we released just now. So the challenge is on QR decomposition, household and transformation, and more. So as I said multiple times, this type of matrix decomposition is fundamental in many machine learning applications, right? From linear regressors to let's say machine learning training and so on and so forth. So constraint optimization is very fundamental. So this challenge will cover multiple aspects of this. So the challenge has 5 different tasks, so it's kind of long. So bear with me. So the only thing that might create problems that I haven't foreseen is this first section, the task, the data classification setup. So I'll describe it next. I didn't have time to check the code, unfortunately, because I always do the challenge based on the discussions in class, so I don't have any backup knowledge. I didn't have enough time to check the code myself. So if you have any problem in this task 2, let me know, and we can change the way in which we generated the matrices. I just want you to understand the application to a certain data set, right? The application of this decomposition to a certain data set. So I try to push this part, even if I was not 100% sure. There is, let's say, there is a 7% chance that it will fail, but and if it fails, let me know. Okay, so the data set for this week is this fashion MNIST. So last week we did MNIST, which again is one of the first data set in history, so it has a historical value. The second historical data set that people look at is fashion MNIST. And as an Italian, of course, fashion is very important to me. So I wanted also to add this cultural declination to the challenge. So it's grayscale images of clothing, right? So there are T-shirts, there are shoes, there are ankle boots, there are skirts, there are whatever. So it's very simple data set, black and white images, 28 by 28. So numerically it should be something that you can handle very easily. So what we want to do is that we want to pick 2 classes, which are the trousers and bags. So these are label 1 and label 2. Also for this, you should have 3K images per each label. So you should have enough images. And the idea is that you choose 2 classes, and then you vectorize the images as you did last time in terms of n times m matrix A. Okay? So this D will be the dimension. It's the original dimension, which is 28 by 28, which is equal to 784. And then you will have a vector Y, which is -1 to 1. Okay, so you choose the first class. Trousers are going to be -1, and bags are going to be +1. Please try to follow this first part of the challenge quite literally, so that then when we go to the presentation and we see the results, then we can compare the results with different teams. You will see that it's nice when when you guys all use the same settings, right? So that we can compare the presentation across multiple groups, right? So try to follow this first section too very closely, so that we all are all doing the same data set, right? So the idea is that we want to find the vector x, which is dimension RD, such that AX is roughly equal to Y. Okay, so the x would be a scoring rule of a certain image, and the idea is that if somebody gives you a new class, right, then somebody gives you a new data set, then you will use this to form, let's say, an A test, right? So a test set of the data set, and the x will be the same scoring vector, so that then you recover this training versus inference setting, right? So this scoring function x that you have learned from this data set will help you do classification for a set of images. Okay. So this is a very simple classifier. Of course, it's a linear classifier. So it's substantially, it's an SVM, right? So you're just finding the minimum, some sort of minimum distance classifier sort. And so it's, of course, it's not going to do as well as an SVM or as a deep learning matrix, but it's just for you to understand and to apply the QR decomposition. So the other thing is that this dimension D, okay, we want to figure out different subsample matrices, right? So we want to take the image and subsample the image in different ways. So then the idea is that we want to reduce the complexity of our inference task by subsampling the matrix. Not take the 728 pixels, takes a lower number of pixels, and see how the accuracy in classifying the two images performs for different subsampling. Okay, so we're going to see next. So this is another point. Please try to implement it as here. So since there is going to be some random subsampling of the images, please fix the randomness, fix the random seed to be this 42. Okay, so you just use these lines, right? So this is something that is very important for reproducibility. So let's say both internally for your debugging and for let's say code reproducibility. If your operations that involve some randomness, usually what people actually not usually what people always do is to fix the randomness in so that if somebody takes your code, they can reproduce your results. Okay, so let me try to make this a little bit clearer. Let's say that you are with your teammates, right, and you are trying to see some specific behavior of the accuracy with respect to some sort of operation, and this operation involves some random sampling. If you don't fix the seed, you will not be able to reproduce this certain behavior reliably, because every time that you turn on the computer, the random operation will change. So how does the computer produces the random operation, right? Okay? So there is a randomness seed, which is initialized at the beginning of your program, and usually this random seed comes from some combination of the time, the current time of the machine time, right? So you take the machine time, you do some random operation, then you obtain a random seeds, and then when the program runs, the randomness is taken from that seed, and then there are different algorithms that produce a pseudo-random sequence from that sequence, and this is how you simulate randomness in a computer. So the discussion is actually very deep, and there is a lot to say on how can you take a single number, between 0 and 1024, and generate a full random behavior out of this. Why do we say pseudo-random? There's a very long discussion about this. The point is that instead of letting the computer pick the seed randomly and then execute the program using this random seed, then what you can do is that you can actually set the seed yourself, so that every time the program is executed, you observe the same pseudo-random behavior of the algorithm, so that somebody takes your code, a colleague or a person that is interested in your project, they can reproduce exactly the figures that you have, the results that you have, and if they want to generalize to some other setting, then they can take that as a starting point. Okay. Again, long discussion why it's important to fix the randomness. Please try to go deeper in this topic by yourself if you're interested. The point is, now we're going to fix the seed, and we're going to use this random seed in order to do subsampling, so that when everybody does some subsampling of the images, we all observe the same randomness. So when we have representation from the different groups, we all see the same images because they start from the same subsampling, the exact same subsampling at all different groups. Okay, longer discussion. I hope I was clear enough. So the idea is that with this matrix A, okay, so it has this n times 784, and this is the full image. Then what we're going to do is that we're going to subsample the image with 3 different levels, so that the matrix is going to go from small and fat all the way to square, all the way to skinny, so that you can see the behavior of different matrices that go from the underdetermined to the overdetermined system. Okay. And this will also help you understand what is the performance with respect to the size of the image A, because we said that in MNIST the images were very sparse, meaning that most of the pixels were 0 and just the few pixels in the center were 1s. And so here instead we have the images are clothing, right? So they are much more dense. So you can see the loss of performance as you subsample. Okay. So what you can do is that you can go full resolution, you can moderate subsampling at 25%, and you can do aggressive subsampling at 10%. Okay. So what you can do is that you can pick the selection at random, right? So you randomly select the picture, or you can take a grid, or you can do some downscaling, or you can crop just the center of the image. Okay. So this is it. These are the settings. So for you have these 4 different classes, right? And then you have 3 levels for classes. So if you do this, you should have a family of 12 matrices, okay, that you can work with. And this will be enough matrices for you to see some sort of interesting behavior. It should not be too many matrices so that your computation takes forever. That was my intention. And then once you have this collection of matrices, what you can do is that you can look at some properties of the matrices and try to have a first understanding how these matrices behave. First of all, is the Frobenius norm, so just the sum of the element squares. So what is the distribution, right, of the weights of the matrices? That they roughly have the same weight, or do we have very varying norms? The spectral norm. I'll let you figure out what are these this object, the rank, the condition number, the smallest singular value, and some summary statistics of the pixel values. Okay, so again, stuff should go there. And the idea is that when you do a classification problem, then depending on how you construct your A, right, with n being the number of samples that you choose, and d being the value subsampling regime that you have, then you're gonna have you're trying to find the x which minimizes this norm. This corresponds to finding the x using the QR decomposition as we have it, and you find the x using, let's say, Gaussian elimination, once you figure out what is the decomposition of A into QR. Okay? And then the idea is that once you have found the X, then you will take some of your test set, and you will see what is the performance in the classification of the elements that are in the test set. And this you can do, you know, you can check the numerical stability, what is the performance of the subsampling, whatever, right? So the different application there. So everything clear now? We have a data set. We find the scoring vector X. Then this X is supposed to create a summarization of the images so that we can classify them as -1 or +1. So when we have during test time, we get an image, we vectorize, we multiply by X. This gives us a number which is a real number. We take the sign of this. If this is if the sign is +1, then it's going to be trousers. If it's -1, it's going to be, I already forgot, bags or shorts, whatever it is. And then you can compute the accuracy of this method. Okay, everything clear so far? Give me a thumb up. Okay, so what we do next is now we take different approaches to the decomposition of the matrix A into QR. So the one that we saw in class was the Gram-Schmidt procedure. Gram-Schmidt in class, we only saw the classical one. Oh, sorry. I always double click and I forget that this is, if I double click, I go to the text. So the classical one, we saw it in class. There is a modified one. The modified one, it's nothing special. You just normalize some things so that you avoid dividing by very small numbers, right? So nothing particularly difficult. So just write the function yourself from QR, please. Write yourself the Gram-Schmidt procedure, and you do the QR factorization, and then you go back. You see what is the accuracy, what is the numerical stability, what is the runtime with the matrix A's that we described before, that we generated before. Then a second method is going to be householder reflections. Again, this is what we saw in class. We said that householder projections are more stable than Gram-Schmidt decomposition because you're not performing an orthonormal construction at each step. Instead, you are sort of reflecting each row into an orthogonal subspace, right, in one of these E subspaces. Again, write it from scratch. Should be fairly easy. Then you go and you finish everything. Then there is a new topic, which is the Givens rotation. Givens rotation, it's very, very cute. Again, not particularly geometrically very elegant. not particularly difficult to implement. So go ahead. Then we get to something cute. Okay, so something cute is as follows: if you have a very big matrix and you want to decompose it quickly, the best thing to do is to try to decompose the problem into multiple problems that you can give to each different processors, right? So the idea is that right now the GPUs are strong because they are multiprocessors. So if you can parallelize a job, you give one job to each processor, so you reduce the complexity by breaking down the problem in multiple instances. And this is exactly what this hierarchical the QR decomposition does. So you have two levels. You have a first level, then you have a second level. Using block matrices, just go ahead and take care of this. It's very cute because first you do a first level of this decomposition of the matrix, and then you can give each of the following submatrices to one of these Gram-Schmidt household or given the composition that you have implemented before. So very easy. Then you can compare the performance of this method according to different blockings, right? So you can block by 2, by 4, and by 16, and you can see how the different blockings perform the runtime. And this should be also very good. You should be able to see numerical speedups you should see some if you manage to use GPU in the program, right? I don't know how many of you knows how to use GPUs, but if you use GPUs, then you should be able to see the parallelization of the implementation. And then so this block and hierarchical QR sort of goes from the numerical recipe to the system level setting, right? So the first level of the class is to understand what is the numerical efficiency of the algorithm. And sort of the second level of the class is how do you implement this on a modern computer architecture where there is a level of parallelization of the job that you can implement. Okay, so it sort of goes one step up in the view of the numerical complexity of an algorithm. And then the last, the task 5 is always the one that goes a little bit further out for you guys. So in this, in task 5, we discussed this, right? So in our QR decomposition, we like the matrix Q because Q is a unitary matrix. So the inversion of the matrix Q has cost 0 because instead of doing the inversion, we just do the transposition. That's why we like unitary matrices. But sometimes it's mathematically more meaningful. It's depending on the application, it's sometimes more meaningful to have that the matrix A is decomposed as a rotation plus a deformation. Okay, so the unitary matrix can always be interpreted as this rotation plus deformation application, and this is very important, for example, in computer graphics, right? Because you can imagine that you have, let's say, an element in the 3D dimension, and they have a certain orientation in space, and so you want to know. What you can do is that you know, let's say, from your graphic engine, the perspective deformation and the orientation of the object, and so you want to apply these two operations separately. Let's say. Or maybe you are seeing a scene, and you know you can interpret this scene in a geometric manner. So you know that there is a lens, right, that determines the deformation, and then there is the orientation of the object. There is something else that you want to extract. This is, for example, is in pose estimation, right? So you have a certain 3D object, you have an image of the 3D object, and you have to estimate the pose. Something else, another application where the composition is very important is in robotics, right? Because let's say that maybe you have some sort of kinematics, right? And you have some inverse kinematics. So you know the final pose of the robot arm, and you want to represent this as a set of rotation per transposition, and so you want to do this decomposition from the objective, the final pose that you want to achieve, and the type of per joint operation that you have to perform. So if you're going to do computer vision, or if you're going to do robotics, you're going to see these topics in more depth, of course. So this is just to make you think of the values of different types of decomposition. And I think this decomposition into polar coordinates, it's very important for you to expand your idea of what a matrix decomposition is. Okay, long story short, you decompose as R times P, where R is an orthogonal matrix, right, which represents rotation, and P is a symmetric positive definite matrix, representing deformation and compression. Okay, so just go ahead and try to see how you can compute the polar decomposition. So yeah. So try to go ahead, okay? Try to go ahead with this task. I'll let you expand it. And then there is the usual stuff, right? So how to write the report, try to visualize your residual, try to compare the precision, blah, blah, blah. Then you submit the report and the slides and so on and so forth. That should be there. Okay? Very good. Any questions so far? Any questions? Any questions? Also, Simon, yes, either Simon or Nofal are going to release the final set of groups, which is going to be hard now to choose people that you haven't worked together already, but it doesn't matter. I just want you guys to get to know each other in discussing the challenge. Okay. Anything else? Any other question? Otherwise, I'll let you reflect over the challenge. And yeah, should be fun. This one should be fun. It's kind of long, but I think yeah, there are many elements which are interesting, and the geometry is very, very elegant. So I think it's gonna be nice. Okay, I'll wait for questions. Otherwise, we continue the class. Okay, good. So now we move to least squares. Okay, so let's go to least squares. So the idea is to finish least squares this week or this couple of weeks, and after that, as I said, we go to PCA, principal component analysis, and there we're going to do a lot of matrix decomposition. Hopefully, after that, we can move beyond some other algorithms, let's say for SVMs, which should be like matrix decomposition is very important, but of course we don't want to dedicate the full semester to this, although we could, because it's a very nice topic. Okay, very good. So let's discuss least square a little bit. Yeah, we take a break after this presentation. Okay, so as we said, also for this challenge, given that we have a linear system and we have to solve the linear system AX minus B, and the way that we want to do it is to minimize the residuals, and the residuals we usually compute them in this L2 norm sense. Okay, so sum of the rows, sum of the columns, ij xj minus bi. Okay, so this is called least squares, right? Because we can see that for each row we have a set of residuals, and these residuals has the Ri, which are contributed to the total loss with the square, and the residuals are row times column operations, right? So you have fixed the I to be the row of A, and then for each of them you have the inner product between the row of A multiplied by X minus B. Okay, and this is called the linear least square problem. We said that yeah, the solution of this depends on the rank of the matrix A, whether A is fat or skinny. No, I always use fat, which is not a good word. Wide or skinny, and depending on these different factors, we can have one solution, no solution, infinite amount of solutions. So this is something that we discussed already. Classic, just a simple example here, right? So one certain value of A, certain value of B, then the least square solution. So you see that A is a tall matrix, right? So it seems to be overdetermined, right? So, but I mean, it could be overdetermined. So we go through here, we put in, these are the residuals. In order to find X, what we can do is that we set the derivative to 0. All right, and the solution that we find, it's just a single solution. Okay, so even if it's a system of 3 equations and 3 and three unknowns, three equations and two unknowns. We are actually able to find a single solution for this, and the way we find this is by setting the derivative to 0. Okay, so this is, let's say, the algebraic ways of finding this. Okay, and notice that setting the derivative to 0 here doesn't guarantee that it's a minimum for us, but we can take a second derivative and make sure that it's a minimum and not a maximum. Okay, so usually we forget about checking the second derivative, the Lagrangian, to know if it's maximum or minimum in this presentation slides. But of course, when you solve the problem, you know that this is it's a concave or convex function, so you can either have one minimum or one maximum. So easy to check. Very good. So, so in general, we want to minimize ax minus b squared. R is the residual vector. R height is equal to 0. Then we have the exact solution. But if we cannot find R height exactly equal to 0, then we have a least square, right? So it's an approximate solution. And so, so that's why we call it the least square, right? Because the solution that provides the least square of the residuals. So we don't say residual, just say least square. But in your mind, you know it's a least square sum of residuals, basically. In most applications, right, m is much larger than n, so ax equal to b has no solution. So you can think about the dataset case, right, in which you have a certain dimension of the entries in the dataset. This is the d, and then you have the n, which is the number of elements in the dataset. Of course, in most machine learning problem, the dataset size is very large. It's much larger than dimension d. Of course, there are some exceptions to this, which, for example, the case of medical records, right? So if you have somebody with a certain disease, it's you have very few individuals that has this specialized disease, but for this individual, you can do a lot of measurements. This is a setting in which this last sentence doesn't apply, but more generally, dataset is much larger than the dimension of the entry. Okay, so we like this geometrical interpretation of this, and we already discussed the range and the span of a certain matrix. So when we're minimizing this residual, basically, right, we have a hyperplane generated by the span of A, right? So this is this hyperplane here. And then the B is a point here. And so what the residual is the distance between a point and a hyperplane, okay? A distance, Euclidean distance, right? So L2 distance. So the hyperplane is the span of the matrix A. And so you take the point which is closest to this hyperplane, and the distance between the point and the hyperplane is defined as the smallest vector, which lies the smallest vector between the hyperplane and the point. And so the smallest vector now we know that it's in the direction which is orthogonal to the span. And so this residual must live in the orthogonal space of the range of A. Of course, everything is in 2 dimensions here. So the matrix A is a span of 2, so that this is a plane, and B it's a three-dimensional point, so it has three directions. So the orthogonal direction can only be 1. So we have one orthogonal vector to our 2D plane. But if we have to go to higher dimension, of course, we will have the same interpretation. Okay? So remember, if you took my previous class, then you remember this example. There's this very other famous data set where you have a certain number of advertising campaigns, and there is a certain budget for demographic group, doesn't matter. But basically, imagine that you have M demographic group, and we have N advertising campaigns. So maybe the demographic group is the age, and whether a person is married or not. And then the advertising channel, let's say they are radio, newspaper, and TV, because we want to stay in the vintage setting where there is no social media influencer advertisement budget. PI is the target number of views of a certain group I. A is the number of impressions the group I per dollar spent on the ads on channel J. And XJ is the amount of advertising and purchase on channel J. And so this is the setting of AX equal to B, right? So what you're looking for is the optimal value of X, which is what you can decide, which is the amount of advertisement that you want to purchase over this. Okay, so here we have the different groups. As we said, imagine this age plus gender. So maybe 1 to 5 are males and 6 to 10 are females. Again, I don't want to go into discussion about how many genders are there. So let's avoid this discussion. We just have multiple groups. And then you have these three channels, and you have the number of impressions per channel. So now you want to maximize the target. You want to know how to match a certain number of views per channel, and you want to choose the budget to do so. So you want to find the X that will reach a certain number of B that you choose. In this case, we choose B to be 10,000 impressions per channel. And so we want to find the X that reaches a value which is as close as to the uniform values of B, so the uniform impression for all possible genders. And we want to find the budget for each of them, and this gives us the X. Okay. Again, 10 different groups, 3 different channels, and the target that we want is to have uniform impression overall. And what is given to us is the number is the matrix A, where Aij is the number of impression in group I per dollar spent in the ad of channel J. Okay, good. So you can imagine that you're sort of trying to choose a budget so that you have the same number of impression per each group, and you have different channels to achieve them. So you have to choose the combination of budget per channel that will achieve this. Okay, and you see that you cannot achieve the exact value B, and because this is unfeasible, right? And so what you have a least square solution, so that let's say how much you miss the mark or you overstep the 10,000 mark, it's weighted with a square contribution. Okay. Another nice example is the illumination example. So that we are given n lamps at a certain position above an area of n regions. And Aij is the illumination in region I if lamp J is on with power 1 and the other lamps are off. Xj is the power of the lamp J, and Ax equal to I is the illumination over region I, and Bi is the target illumination over all the region. Okay, so you have this area, you have multiple lamps, you can decide the power of each lamp. The power determines the illumination, and so you want to have a certain illumination of all of the area. Of course, uniform illumination is something desirable. And so this is the geometric interpretation. This is the position of the different lamps. And in each of the squares, we have the corresponding illumination. Of course, illumination is additive, right? So you sum the illumination from different lamps. And then we try to solve this as a least square problem. And here there are just some examples. You see, of course, we want the illumination to be uniform all over. And then we sum the loss from this uniform illumination using a square, which seems to be reasonable. And then you see here the different solutions that we have. And you see that you have the 100 regions, so it's a 10. Is this log? Okay, so let's just say it's a 10 by 10 square. And then you have the illumination which you achieve over this. And then given the different location of the lamps, you have a different intensity. And you can just solve the problem in this way, right? So the X now is the energy that you provide to each of the lamps. Okay. Discuss the solution of a least square problem. As we said, the general approach to solve the least square problem is using the pseudo inverse, and we like the pseudo inverse because it doesn't distinguish whether the matrix A is tall, wide, or a full rank or not full rank. It's a generalization of this. So remember, it's A transpose times A to the minus 1. A transpose A is a square matrix, and it's symmetric, so the inverse is always nice and well defined. Then you multiply IT, and then this is the unique solution of our AX minus B square. Okay, so we have a closed form solution for a minimization problem. And as I always tell my students, this is a blessing from the gods of engineering, because of course, it's very rare for a minimization problem to have a closed form solution. It happens basically 3 or 4 times per 100 papers that you read, let's say. But remember that the properties of this is that if we take any other x which is different from our optimal x, then the residuals are going to be larger, strictly larger, okay, strictly larger in this case than our minimum solution. Okay, and we call this the pseudo inverse and of a left invertible matrix. Okay, so remember that since matrix multiplication is not commutative, then we're going to have left inverse and the right inverse. Very good. Yeah, just a simple proof here. What you have to return, what you have to remember for this as this orthogonality principle. Okay, so let's should we go through this? Okay, I'll let you go through the proof, but basically, so I'll just tell you what's important about the proof. What's important about the proof is that the residuals, they lie on the orthogonal space of your span. Okay, so you can imagine if you had any other solution by this orthogonal solution, the residuals that you have, let's say there was another x here. So we're not taking the optimal x, we're taking another x which lies somewhere else. The issue is that the residuals, like this vector r, will not be orthogonal to the span. Okay, and so you will have a component which is orthogonal and a component which is parallel to the span. And of course, this component which is parallel to the span can have any sort of energy, right? And so you can never reduce the energy that you have in the orthogonal directions, but you can reduce the power that you have in the parallel direction, and that energy is minimized when it's set to 0, right? So if you take the point for which the residuals, they all live in the orthogonal space of the matrix A, then that's when it's minimized. Okay, so the proof per se, it's very simple, but again, what you have to remember is this, what is called the orthogonality principle, right? Which says that the residuals in the least square problem, they live in the orthogonal space of the matrix A. Okay, very good. Of course, we can also do a calculus derivation, and the usefulness of the derivation in the calculus perspective is simply that it teaches you what is the derivative of a scalar function with respect to a vector. Okay, why? Because ax minus b squared, this is a scalar, so it's a dimension 1, but you want to take the derivative of this object with respect to a vector. So you have to ask yourself, I have studied for 23 years in my, well, okay, I studied for 16, 15 years in my life, and I know very well what is a derivative of a function with respect to a single variable. Now, how do I think of the derivative of a function with respect to a vector? Of course, the math works out exactly as you expect it to be, meaning that the rule of derivation, they go from the derivation from a scalar to a derivation with respect to a vector. They work out exactly as you expect they are. You just need to have the correct mathematical formulation so that you know how to apply these rules in the correct way. So since we're engineers, the vector x for us is always a column vector. This is our standard. If you were a statistician, then x will be a row vector. Remember that if we set our x to be a column vector, then the derivative of a function with respect to a vector will be a row vector. Okay, so this is a scalar function. So we form this nabla of the function f, which is a row vector that contains the derivative of the matrix partial with respect to each of the coordinates of the vector x in a row. Okay, so what is now the derivation rule, right? So this is like a quadratic function in a higher dimension. Okay, so x is a vector, and we have this orthoquadratic function. So we imagine it as a ball. Okay, then we take the derivative with respect to the vector x, and the derivative of this object is exactly the version of derivative of a times x squared divided by derivative with respect to x. So you should get something like 2x. Okay, so instead of getting 2x, you get 2a transpose multiplied by ax minus b. Okay, so you can derive this explicitly by considering the derivative with respect to each of the component, and then building this nabla component by stuffing in each of the derivative with respect to one of the xk, and then figure out which vector operation this is. So if the derivative with respect to a single component of vector x will contain only the kth components of this object, right? Because all the other derivative, all the other xj will be set to 0. So of this summation, you just keep the kth component. Okay, so you fix k here. This is like you fix the j equal to k. So only the j equal to k component remains, and this can be written as the k entry of the a transpose ax minus b component, so that when you then build a vector like this, you just have to remember that this has to be a row vector, and this is what comes out. Okay, 2a transpose multiplied by ax minus b, and this in your mind, right, with your 2D intuition of the word, this is like the rule that says that a times x squared is equal, derivative by x is equal to 2 times a times x. Okay, you just have to remember that this goes, and when you use this often enough, then you just remember these rules by heart, basically. So the geometric interpretation is as this. So the residual vector r hat is equal to b minus ax, and remember the orthogonality principle. So if we take a transpose r, this must be equal to 0. Okay, and this is because the component which is left is b minus a times x, and this must be orthogonal to A. So when you do the product, then this must be equal to 0, which is the residual vector r hat is orthogonal to every column of A. And so it's orthogonal to respect to all the range of A. Okay? So the projection on the range of A is a linear function with coefficient of the matrix A multiplied by A transpose A to the minus 1 A transpose. And this is equal to A times A tag. Okay? Very nice, very elegant, very cute. Yeah. Very good. So how do we solve the least square problem? So we see that we want to solve, we can multiply, doesn't matter. We can bring the minus 1 to the other side, right? So that we have the equation A transpose A times X equal to A transpose B. These are called the normal equation in the least square problem. And the coefficient of the matrix A transpose A are the gram matrix of A. Okay, gram as in Gram-Schmidt, of course. So when this is equivalent to setting the derivative to 0, where the derivative of f to 0, where f is the residual equation, and all the solution of the problem are satisfied the normal equation. If A is linearly independent column, then A transpose A is non-singular, and then the normal equation have a unique solution. Okay, and as we said, we do this with the QR factorization. So we already said that the trick is that the matrix Q is an orthonormal matrix. So when we do this inversion, this object becomes a Q transpose, and then the r to the minus 1 goes away, and we are left with this, right? So basically, we have to take the r to the minus 1. R is upper triangular, so the inverse it's very simple. It is very simple to compute numerically, and the Q transpose is only it's very easy. And so yeah, so this is the complexity that we discuss. Some examples. Everything is good, and this is the story for now. Okay, very good, guys. Let's take a quick break, and then we come back in 5 minutes, and then we go with the lecture. Okay, drink some water or some coffee, like in my case, and then we are back in a second. Okay, I'll see you back in 5 minutes. Okay, guys, we are back. Do least square and data fitting now. So we're still following the slides from the UCLA course because I really like the authors. They are very numerical optimization oriented people. We're going to move on to some other set of slides for the next topic, SVD, but I'll let you know as we go along. Let me grab my coffee. Okay, good. So another since it's midterm week, it's pretty light lesson, I think. See how it goes. So now we want to bring back this keyword decomposition more toward the data science perspective. Okay. So as we said, we want to look at this y approximately equal to f of x. So x is our independent variable, our observation, y is our outcome or the response variable. And we have a certain class of f that we can determine. The idea is that we want to fit our data to a certain prediction, okay? And what do we have here? We have that the data is consisting of n samples, which are our observations. And what we do is that the observation is dimension d, and we stack this n observation into a matrix, okay? And same for y. Y are our label, and we stack them in a vector. So then now y is equal to a of x correspond to the model, correspond to the model that we have, meaning that y are our response variable, x are our input of the system, and we want to find the matrix A that better determines the relationship between the y and the x. Okay, and in order to do that, we choose that we're going to penalize the error between the true label and the label predicted by our model, which we're going to call y hat, in a square manner. Okay, so we choose a penalty which is the square of the residuals. Okay, so this is a choice of loss that we have as algorithm designers. And as algorithm designers, we have also chosen that the mapping between the y and the x is going to be a matrix multiplication and a find function. And so this is the machine learning setting for this problem. Okay, so the model f hat is going to be determined by the finding the matrix A, and the data A fits the data well under the residual Ri being small. Then now the prediction error can be quantified using the mean square error, MSE, which is the sum of the residual square. Of course, MSE has different names or different forms. If we take this if we take the square of the residual instead of the MSE, then we call the RMS. It's more used in statistics. And yeah, so you can also remove the scaling by n. Then you have the sum of residuals, and this is something that you guys are going to see for sure. So anyway, so different ways of formulating the same loss that doesn't change the optimization procedure that we have described so far. Okay, so let's go to regression. And so in this case, we consider a linear regression model in which our f hat of x is going to be x transpose times beta plus a certain nu. So we treat x as the independent vectors, which has and a small n dimension. I prefer, you can also say that d is the dimension of the observations because d is the dimension of the problem. Just choice of names for parameters. And the elements of S are called sometimes the regressors. The model is parameterized by the vector B and by the offset nu. And the prediction error is Ri, which is y high. So the ith entry in the dataset, f hat x of I, which is equal to this yi minus xi transpose beta minus nu. And the MSE is this equation here. So this problem goes back to the origin of mathematics, basically. Yeah? Then we have we have to choose the parameter nu and beta, so that the MSE is minimized. So it is very inconvenient to carry around this nu and this beta separately, right? Because of course, to have a more compact matrix notation, we would just like to have an AX equal to B. So how can we bring the nu inside? What we do is that we augment the data set by a constant feature, which is all equal to ones. Okay, and this forms this matrix A that we have here. Okay, so this matrix A is a constant vector of ones, and then we form a theta, which has the nu as the first parameter, and then after this we stack the vector of beta, which depends on the dimension, and this gives us this this vector y of dimension d. So that basically we have simply rewritten in the matrix form nu plus x transpose beta as ax multiplied by b. So I don't know if you've seen this formulation already in your high schools, depending on the, yeah, I don't know exactly the Taiwanese high school system, but this is a very common trick that simplifies the matrix notation. Very good. So now that we know that we don't have to carry around this nu separately, we can form we can have a very compact matrix notation. So let's see some example. This is another classic data set, which is the house price as a function of the number of just a second. So y hat is the predicted sale price, and y is the actual sale price. And you have two regressor. Xi is the house area, and X2 is the number of bedrooms. This is another classic data set from, I think, the US government in the 1930s or something. And let's say that we have 774 house sales, and then we find the best RMS the best RMS, and this turns out to be 78 plus $4, since it's the residual will be dollar squares. And if we take the square root, then we get it in dollars because we lose the square. And so you see here the representation of the learning problem, right? So you have the actual price, and you have the predicted price, and you can see this scatter plot, and this is the line that determines the x equal to y. So if your points, right, they very much align around this diagonal, let's say in a symmetric way around this diagonal, then you know that the linear model captured well the pattern in the data. Here you see that there is a variation from this intercept at the low level, right, at the low price. So it means that for the low actual price, then the linear approximation is only partial. Because your model is over predicting these prices, right? So you see that when the house should be 100, your model is predicting 150, so it's overestimating the price of small houses. But of course, this is the best. This is the best least square solution. This is the least square solution, so it's the best solution in that sense. So now we can add more regressor to see if we can get a better prediction. So we said that x1 is the area of the house, x2 is some other variable, x3 is the number of bedrooms, x4 is whether it's a condo or not, and x5 to x6 is, let's say, 4 groups of zip codes. So now you know that something interesting is coming up, correct, right? Because let's look at this variable. For example, the zip code, right? It no longer has it has a categorical interpretation. It's no longer a quantitative variable or some sort of sample quantitative variable, because the zip codes, right, they cannot be aligned over a line, right? That you don't have a partial order of the zip codes, right? So you cannot say that a certain zip code is naturally higher than another zip code. So we lose sort of the L2 nature of our input variable, right? Now we are trying to incorporate some categorical variable into our model, and we have to ask ourselves if it doesn't make sense that our model takes a certain value, takes a certain range, right, which we put in the model. For example, right here we choose, you see that there are 4 different locations, And what we do is that we do a one-hot encoding on the location, meaning that if the location is A, then we set everything to 0. If this location is B, we set the first variable to 0. Certain variable C is the second one to 0, and the variable D is another one. So we have what it's called one-hot encoded the location into a binary variable. So now in your mind, as an algorithm designer, you know that you have taken an affine function, so you have chosen a linear scaling, in a sense, a linear mapping between your input variable and your output, y, and you're trying to do a mapping of this quantitative variable that you have encoded as a one-hot encoding into your prediction of the price, and you have to make sense of whether this operation is meaningful. And here, notice that also here x4 is a binary variable on whether it's a condo or not, and this is 0 if it's a 0 if it's not a condo, y it's a condo. So now you have, of all the possible type of houses, you have also selected one categorical variable to determine the price. So very good. And now you can do the fitting of this, and you can see that your model now it's doing less of a prediction on this area here, right? Because maybe it turned out that condos in certain areas, they had some specific lower price, blah, blah, blah. So your linear fitting has improved, and your RMS error now is also decreased, okay? So, so there is some more discussion to do on this and some more thinking to do of what is the meaning of associating a coefficient, let's say a real coefficient to a categorical variable. If you take my Python machine learning class, then you can dig more on this. Linear in-parameter models, okay? So if we choose the FAT to be a family of models, okay? So now we have that in our prediction function, it's a certain weighting of other prediction function, f1 to fp, right? So the function fi's are scalars, scalar valued basis function. So we can choose a certain set of basis function, and this basis function often include a constant function, which is the f1x equal to 1. So there is a constant function. And θ1 to θp are model parameters that we're trying to learn. And the final model that we have, this final FAT model, it's linear in the parameter θi, so that we can run an optimization on our θi. So if we fix the first one to be the constant function, then we can interpret we can interpret this model as being as the regression model of y hat equal to b transpose x tilde plus nu, with parameter nu equal to θ1. So this is our constant coefficient, and b is the second version from t to p, and x tilde is f2 of x, and xp is fp of x. Okay, so it's as if we say we have this general family of functions. We chose the first one to be a constant, and all the others to be a function that considers only the p variable of the vector x, and then we apply linear optimization. But of course, we can have a more general formulation in which these f's are chosen more freely, and they are chosen to be basis functions, so they are orthogonal. Okay, so when we have this formulation, then we can have a linear in parameter model to the data, and the residuals are determined in this way, and then the theta's are again determined by choosing the mean MSE, and then the least square problem is formulated in this way, right? Where the vector f, the matrix A is the evaluation of the functions from f1 to fp over the dataset entry x1 to xn, and the thetas that we want to find are the θ1 to θp. Okay, so now we have found a more general linear model to use, and we can play around with this. So in a sense, you see that the complexity of the function f is sort of abstracted out, right? Because in finding the parameter theta, we are only evaluating the functions on one of the dataset points. So in a sense, we can construct these f's the way we want, given that then we remember that in order to find the theta, we are evaluating this function on one of the dataset entries at the time. So even if the F, let's say, is very, very complicated, this doesn't account, this doesn't play a role in finding the parameter theta, because we are just interested in the evaluation of the function F in one of the dataset point. Does that make sense? Okay. Okay, good. Now we can change, now that we have this thing here, we can switch up things a little bit. And for example, what we can do, instead of considering just the vector x of observation, we can take multiple powers of the vector x. Okay, so now this is sort of a dumb thing to do and a smart thing to do. So it's dumb in the sense that if we have a certain data set of observation x, what is the value of taking the vector x and taking the square of this observation, taking the q, taking another power? Do we expect that new information to be generated when we take take a certain power, a certain function of our x? Of course, in our mind, right, these operations, they don't generate information, right? We are not enlarging the data set. So how can we get a better performance if we take a power of the data that we have? Doesn't seem to be very smart. But actually, what we're doing is that we are trading off, right, the complexity of our linear model with this augmentation of our data set. Meaning that now, when we form the matrix A, right, in the matrix A, we can have our constant coefficient, will give us the nu, and then we can have multiple powers of x, and this corresponds to not fitting now a linear function by a certain polynomial function. So we have artificially augmented the number of observations that we have, and we have done this in order to move from a linear model to a polynomial model. Okay, so it is actually conceptually very simple, because what we gain is that we still have an efficient way of finding our parameter theta, so that we pay the price of enlarging the data set by considering not only x, but also a certain amount of powers. But now the solution of the parameter thetas still remains simple, because the matrix dimension have been increased by this amount. But this is generally a numerically efficient solution to solve. So we did, in our mind, we did a good trade-off between complexity and performance of the model that we have. Good. So now what we can do is that we consider different set of p values. I call them pitas. That's Greek food. So we can increase the degree and see the different behavior of the model with different values of p. And as you can imagine, p is a hyperparameter. So we have to tune this parameter p, this hyperparameter p, to be a meaningful value that performs well in our set. And as I often say, if somebody gives you an algorithm with a hyperparameter, then the problem didn't become any simpler, because now you have moved the problem of finding the model to the problem of finding the hyperparameter that controls the model. I mean to say this: we started with a linear model that didn't have any hyperparameters, and we found a solution. Now we said, oh well, we can add this polynomial approximation. You just have to choose the value of p which is good for you, and find the p value that performs well for us on this hyperparameterized problem is just as difficult as finding the linear problem. So adding the hyperparameter didn't remove the complexity of the problem, and we just transformed the complexity of the problem. Now, how was the complexity of the problem transformed? Now we added more parameters to the model, and the risk of having a lot of parameters is that you are overfitting your data set, meaning that once you solve the optimization problem, you're not finding the pattern which is inherent in the data. What you're doing is that you are fitting the specific instance of the data set that you have using the extra parameter that you have. Let's go to here. Let's say that we have this type of scatter plot for our data. Okay, so this is our x, and this is our f hat, and this is our y. So we're in a a two-dimensional setting, let's say. So we have y's and we have x's. We have one-dimensional input and one-dimensional output, and we plot the data set as a scatter plot. So these are all the xy pairs. Of course, this is a simplification to the two-dimensional case, just to give an intuition. So you see that this is the scatter plot. So in our mind, we see that there should be some sort of, sort of smooth polynomial interpolation of these values. So if we do a linear interpolation, right, then we're going to have a lot of residuals because we are missing sort of this high and low areas of the data set. So what we can do is that we can choose the first P, and you see that this P doesn't do a very good job. So we can increase the P to 6, so that now we have a function that has multiple maxima, multiple minima, and we can find the coefficients of the polynomial so that we match these two maxima and then this one minimum. But then we tell ourselves, why don't we just keep increasing the P? And the issue is that if you keep increasing the P, your residuals are always going down because you add more parameters. So you have a larger family of models that you can fit to the data. But of course, you see that as the P increases, then you start fitting the specific elements in the data set instead of the pattern of the data set. But of course, we have no way of formalizing, right? What does it mean to overfit the data? Because we do not know what the pattern of the data is, because if we knew it, then we wouldn't be here struggling trying to find the hyperparameter. Okay, good. Now, polynomials are good. Another thing that we really like are piecewise affine functions. So we like to have a function which locally performs as a linear function, and then we have different switching point between in our data, so that then we can have a combination of piecewise function, and with piecewise function we can have many different a large family of functions that we like, meaning that locally we can optimize the function efficiently using our closed form solution for linear function. If we go to the polynomial interpolation, then we know that polynomials are very smooth locally, and we avoid the problem of using polynomial over large intervals, because polynomials, if they have large coefficients, then they behave, they have very large jumps of values over large intervals, and this is something that we don't like. Okay, so think about a polynomial, right? A polynomial always go to either plus infinity or minus infinity as we go to x minus infinity and plus infinity. Okay, so a polynomial is always coming down from infinity or going up to infinity. And this is very undesirable because, let's say, if there is a range of input that you haven't observed, which is far away from the range of input which you have, over which you have constructed your data set, your model is going to explode. So by their own definition, linear models, they explode at the edges. And if you are not sure that your model it's going to encounter some extreme values of x, then you cannot guarantee that the polynomial function is well behaved. So what you can do instead is that you can chop up your interval, and then on each of these intervals you can have a well-behaved polynomial function. Okay. So what we want to do is that we want to define a set of knot points from a1 to ak on the real axis, and then you want to have a piecewise affine function of each of the interval ak to ak plus 1. So in the piecewise affine function, you have the knot points a1 to ak, so that we have a f hat of x, which is this beauty here. And we take the function u, which is the max between u and x and u and theta, and this is the usual ReLU. Okay, so 1 plus 1 ReLU and 1 minus 1 ReLU have this nice formulation, so that you can write the affine function as follows: f1 of x will be equal to 1, f2 of x will be this, and then the f3 of x is this, and so on and so forth, right? So you see that this u function will kick in from a1 onward, right? And so that this reconstructs the affine function. The way I imagine is that you have a function which is 0 until the not, and then it becomes an affine function. So by stacking these affine functions, you can successively build your ak to ak plus 1 functions, okay? Because each next fk will, let's say, erase part of the contribution of the previous fj with j less than k, and then add some sort of new linear contribution. Okay, so if you can do this, and yeah, you can find your affine fit to the function, so that it's as we said, it's a nice family of function to play with. And of course, this model, you just have to deal with the fact that when you build your matrix A, then you're evaluating this matrix A over this nonlinear function, because the linear function U is nonlinear. But apart from that, there's no particular numerical complexity. Good. Some example with time series. So let's say that we have n data samples from a time series yi, where yi is the value for time I, and we have n time instance. And we want to find a straight fit line, which is the y hat is equal to theta 1 plus theta 2 plus I, and this is what we call the trend line. Okay, so in the residuals, they have this nice formulation where you have yd minus y hat of d, which is the sum of the data, which is called the d-trended time series. So if there was a linear trend in the time series, you want to build another time series where you have removed what is a linear pattern in the data. And this is very common. This is very common in, for example, if you have energy consumption. Okay, so if you have, let's say that you have a very long, literally like 10 years of energy consumption as a certain city, the energy consumption of the city is always going up because people have more and more electrical appliances, and the steadily but constantly people add electrical appliances to their house. So if you see the energy consumption of a city, there is often a very clear trend of linear increase of energy consumption. So let's say that now you want to do energy prediction, and what you want to do is that you want to predict the energy consumption as a function of the weather and as a function of the days of the week. For example, the presence of holidays and so on and so forth. So you want to do some further analysis, which involves maybe some other variables that are more easily observable for you. So often you're very happy to take your energy consumption data and de-trend it, so that then the periodicities and the regularities and the correlations they appear more clearly in the model. Okay, so for example, you want to see the correlation of the Monday energy consumption of 1 year with the Monday energy consumption of the other year. Your correlation will be affected by the presence of this underlying trend of increasing energy consumption. So if you remove this initial trend, then it's easier to see the correlation plot by simply doing a convolution of the time series with itself, with a certain gap. Very good. So so you do want to do a least square fitting. So what you do is you construct the matrix A in that way and the matrix YD in that way, and then you just solve it. Okay, so let's say this was your petroleum consumption. That's another good example, petroleum consumption. So you see that the petroleum consumption is always trending up. Also nowadays, the reality is that we use the petroleum more efficiently, but the total use of petroleum is always increasing. So if you do a detrending, right, then you see better the pattern of the detrended data, and you see the various wars and OPEC and other political Strait of Hormuz and the other events that have affected the oil consumption has removed the larger trend of increasing energy consumption. This is what we were discussing before. So if we have a linear seasonal component, this is the case of electrical consumption often, and also for petroleum consumption. Then you see that you have a linear component plus a seasonal component. The seasonal component you will figure out using a convolution of the of the y data with itself with a certain gap tau, which conforms to your seasonality. And so if you remove the linear component, then things get easier. And this is again a vehicle miles travel in the US per month. Of course, people are using more cars, are working further away, whatever. So there's always an increasing trend. If you detrend it, then you see more clearly a pattern where people use the car more in winter, and they take less trips in winter, and they take whatever. Good. More beautifully, we can move on to linear filters. So autoregress is a series time model. So now you have that your current estimate of the time series is a certain filter version of the past models. So you say that z hat of t plus 1, it's a function of beta 1 zt all the way to beta m zeta of t minus m. And this is simply a linear filter. This is a convolution. This is a convolution operation. Some of you guys are going to see this in signaling systems. So I'll let these classes expand more on how to analyze its systems, the stability, poles and zeros. It's not my job in this class to teach you this. So the idea is that we have a certain time series, and then we want to find this type of autoregressive predictor of the time series as a function of t. And again, this has the idea of removing some memory which is in the data. Okay, so let's say that you're looking at some weather temperature, some temperature data, right? And you know that, for example, the temperature of a certain day has a certain correlation with the temperature of the past week, let's say. So what you want to do is that you want to detrend your data from this so that you can account for the memory of the system and remove the memory of the system from your data, so that when you look at the data, you can see it without the memory, and you can just see the independent contribution of each day, for example. Okay, so this is autoregressive model. It is called autoregressive because the current value depends on the past values, right? So the past value of the process itself. So the regressive part tells you that it's linear dependencies. The auto one tells you that it's regressive on your own values. And the way to solve this using our beautiful regression model, linear regression model, is to just construct the matrix A as follows. So we have the memory for each time instance. So a Zm all the way to Z1, Zm plus 1 to Z2, Zt minus 1 to Zt minus m. Okay, so you have your time series. You skip the first m data, right? And then you regress from the first Zm all the way to Z1. Then you look at your m plus 1 and you go to Z2. So as if you have this value, this window of length m, and you create a data set for all possible window values. And then you put the coefficient b1 to bm as your betas, which you want to find, and then the y values, they are matched to the future. Okay, so at time m, we are predicting the time m plus 1 using the past m values. Okay, so the y will be the m plus 1, and what you have in the window is the zm all the way to z1. Of course, these are all parameters that you can change, meaning that you can change the past window the way you want. You're still going to have a linear system, and you can change the way you predict the future the way you want, right? So you can predict 1 instant, 5 instants in the future, 10 years in the future. You can put everything, and for whatever setting you choose, you're going to have an efficient algorithm to determine your beta values. Okay, so your b1 to bm. Hourly temperature in LAX, and as we were saying, the temperature in the day, this is 1 day, 2 days, 3 days, 4 days. So you know that the model has a certain memory, right? There's an inherent memory of the system. The weather can change on an hourly basis only so much from the previous pattern. So the memory M is fixed to 8. Here you predict 1 hour ahead. And so you can feed the data, and you can see how well the autoregressive model performs, right? So the memory of the data is significant. And given the temperature in the previous 8 hours, you can quite confidently predict the temperature in the next hour up to a certain innovation, right? And this innovation gives noise on top of the prediction based on the wind. Very good. Validation. So the ability to predict a model from the outcomes of new and unseen data is called generalization ability. So when people say, "Oh, this model generalizes very well," or "this model doesn't generalize very well," which is most of the times what you have to discuss, is you have to choose a set of validation data, so data that has not been shown to the method before. So the data is divided in training set and test set, which we already discussed in the previous challenges. So you train the data on the training set, and then you study its performance on the validation test. And as we said, a model overfit if the prediction on the training data is always low, but the error on the training set is large, and this means that the generalization error is pretty large. So this is the figure that you always want to see when you try to choose your hyperparameters. In this case, we have the degree D of the polynomial fitting. As we said, as D increases, we add more and more parameters to the model. So the model will find those parameters that feed the specific data in the data set. And so this is the classical plot that you want to see. As the number of hyperparameters increases, so in this case D, then the training error always goes down, but the test error has a sweet spot, right? So you see here that this is the sweet spot, and if we increase the number of parameters, then the error on the test data is actually increasing. So you're always looking for this point. Of course, it is very difficult to find this spot because you are consuming a lot of computational resources, right? So you would like to avoid having your optimal value being 5, and then you have to test to a parameter. You have to do the optimization all the way up to 20, right? So it's sometimes. So it's easy to have this plot for learning problems for small dimension, but of course, it is very expensive to learn this performance on a very complex model. Okay, very good. As we said, overfitting. If you look at the residuals are not distributed around 0 most of the times when you are overfitting, because you are, it is clear why, right? Because you are not following the exact pattern, so that the error doesn't average out to 0. So usually you do a histogram of the error, and you see if the histogram is centered around 0. And sometimes it's not enough to just looking at train and test data, because you will not want to see only the performance in terms of the exact value, but you would like to have a distribution of your errors. Okay, so we don't have time to discuss this too much in details, because there's always too much to learn and too little time to learn it. The idea is as follows. We want to repeat the train and test operation multiple times over a randomly initialized set of training and test data, so that we collect more observation about the error committed over each of the random initialization of the algorithms, and then we can have a distribution of our parameters. And from the distribution of our parameters, we can see if the distribution of the parameter is very narrow or it's very wide. If the distribution is very narrow, it means that however I choose my train and test data, the optimization procedure always finds values that are consistently close. And if I have a large error on the estimation of this parameter, it means that I cannot really test. I cannot really rely on it, because as I randomly initialize the train and test data, I get very different values for this parameter. So this parameter is not really fundamentally relevant to my estimation. So what do? We call this false. We have a data set, and we randomly choose a training test and a test set for each of the faults. And then for each of the faults, we're going to repeat the same optimization procedure, write down what are our model parameters, write down what is our RMS error, and then we create an histogram for this. In this case, we have 5 faults. For each of the faults, we find the parameters, and you see that we observe a certain distribution of the parameters, and we already know a lot about this, okay? So our B1, very, very consistent, around 160 to 170, okay? Our B5, very consistent, around 100. What does it change a lot? Let's say yeah, they're all pretty good. Maybe this one here is a little bit tricky, right? So you can go from 17 to almost its double to 29, right? So very large. Train error and test error are pretty good. So what we can do is that we can create a histogram for all this, and we will see what is the mean value and the variance. And then if one of these columns has a very large variance, then we know that this is not really a model, it's not really a parameter that we can trust to consistently give us a significant contribution to the estimation. Very good. List square for classification. Guess that this is exactly what is the challenge for today. Okay, so you have two-way classification. So you have 2 classes, then you want to distinguish between 2 classes. So we go from regression to classification. So we have a Boolean classifiers, and we want to use a least square model in order to do prediction, in order to classification. And how do we do classification? We have X transpose B plus nu, which give us this F tilde. And then what we do is that we take the F hat to be the sign of the F tilde. Okay, so the sign can be either +1 or -1, and usually, if a number is exactly equal to 0, then we put this as being sign +1. We already discussed this. What is the sign of 0? For us, sign of 0 is plus. Of course, it's very hard that a numerical model gives you exactly sign 0. So this is the case that we already did. M is data set. We want to classify. Just 2 digits. Okay, we have 60,000 training data, and then we have 10,000 test data. We use the pixel that are non-zero, right? So this is something that you also guys figured out, that the pixel at the edge are always equal to 0, so you can just trash them away. And this is also part of the challenge for today, is how to drop some of the pixels. And we want to have a binary classifier that distinguishes the digit 0 from all the other digits. So the classifier is 0 versus other digits. And we build a linear model, and then based on these 492 intensity pixels, and we can plot the distribution of the errors as a function of so this is the F tilde. Okay, so this is our is the linear function before the sign. Okay, so this is the soft output of the model. So you see the soft output of the model goes goes negative and positive. So the zeros are assigned in the -1, and the positives are assigned to all other digits. What we do is that we can go through the test set and see for the test set what are the values that are produced by the model, and you see that all of this. Right, so this will be all false positive, and this will be all false negatives. So the blue bars to the left of the dashed line, these are false negative. So these are digits that are non-zero, which are classified as 0. And the red bars to the right are the false positive. There are the digits that are non-zero, which are classified. The digits that are 0 that are classified as non-zero. And you see that you have a nice smooth distribution, right? So easy peasy. And then for each data, we can decide what type of error we have. So we have +1 that remain +1, which is called then true positive. Then we have -1s that remain -1, which we call true negative. And then if a +1 goes to -1, then we call it a false negative. And if a -1 goes to a +1, we call it a false positive. Then we can repeat this on training and test set. We can see what is our error rate on the training set and the test set. And what we can do is that we can add some nonlinear features. And we can create some random features. We can create additional features on this, and the additional features that we produce are this random are x plus si. So we randomly generate, let's say, a vector r of weight 1, and we do this random projection of x over r, and then we add a random shift. And if we do this with 5,000 functions, then our linear model is going to pick some of this linear projection and decide that they're very relevant for the estimation. And so if we're happy to augment the model with some random projections, then you see that we obtain a much better prediction of negative and positive and negative, zero and non-zero elements, digits. And this is something which is a good lesson for us, right? That if we let the algorithm choose the coefficients for the linear model, then the coefficients of the linear model, they're going to reflect the importance of the feature, right? So features that are more important are going to achieve a higher value. So by looking at the output of our least square, we can decide which elements are relevant and which one we want to keep and which one we want to throw based on the cross-validation procedure we described before. Now the error rate goes down. Because we had added the 5,000 random function to the model, so it's a more complicated model, but it has better performance. So there's always a trade-off between complexity and performance. And what happens if we want to do multi-classification? So far, we were happy to distinguish between zero and non-zero function. Then we have to ask ourselves, well, if we're actually detecting zeros and non-zeros, zeros, or the digits between 0 and 9, how are we going to build our estimation? Of course, there are different ways of doing this, and there are ways that are dumber than other ways. And a dumb way to do this will be that you just take the closest integer to the linear model. Of course, what you're hoping is that if you have a number, right, which is if you have what you hope is that you have a linear model that produces something close to 5 for all the input value 5 and something close to 6 for all the values that are actually 6 in the data set. But you understand that this model doesn't perform very well because the linear function, right, the affine function that we choose is sort of a smooth transition between the labels between 0 and 9. And you have no way to believe that the handwritten digits, they smoothly transition between, let's say, 1 and 2. Of course they don't, right? There is no idea of a continuity in the input space between the labels. So try to have one linear function that predicts multiple labels. It's usually a foolish idea, even if you allow for permutation of the labels, let's say. What makes more sense is to have actually 10 different classifiers and have one classifier to detect whether a digit is 0 or non-zero. And then, right, you will have the output of multiple models. And since the models, they output a confidence that a digit is a certain number versus not being the number, then you take the output will be the largest confidence, okay? So the f tilde of k will tell you the confidence that a digit is k versus being not k. And then you do this 10 times, and you choose the one that has the highest confidence, okay? Of course, this is a very high level, very high cost, because now instead of having one linear function, you have 10 linear functions, and your performance is better. So again, depending on the setting, you might have to live with a certain trade-off in which you do this. And for example, you could, as we saw in the last presentation, right, you could have some sort of hierarchical setting in which you classify certain clusters, and in the case, the number of linear model it's much smaller. Okay, here this is the MNIST. You have the MNIST confusion matrix, right? So this is the prediction, and this is the actual values, and you can see the I think we know this very well, right? Which digits are most often classified other digits, 7 as 9, 3 as an 8, right? Where is 3 as an 8? 3 as an 8 should also be large. No, actually, 2 as an 8 is very large. This is not, yeah, this is something that we expect. And statistical interpretation, as we said, we expect the model to be a linear function, and then in order to account for the residual, we assume that the residual is some additional noise epsilon. What we ask for this epsilon is to be an independent disturbance, which does not depend on x or over y. And so the assumption is that the noise is zero mean, and it has a finite variance, and the disturbances are all randomly observed in each element in the data set, so that we have an exact solution, and then we have a random perturbation. And so when we do the orthogonal projection, we are minimizing, we are actually observing the statistical error which is added to the model. So if we take the expected value of this error, it should be 0. And if we look at the correlation matrix, it should have this form, where the correlation matrix is across the different dimensions. Okay, so our gram matrix correspond to the covariance matrix of the error, and it corresponds to the correlation between the I component and J component of the error. Okay, so the error is independent from dataset entry to dataset entries, but over the dimension of X, so there could be a correlation of the error, and this error can have a certain covariance matrix. Yeah, then we are estimating what we do when we estimate the residuals, and actually we estimate the covariance matrix between the noise entries in the different dimensions. Profits here, yeah, just easy stuff there, just easy stuff. And in this statistical setting, then the matrix P becomes the best linear estimator of y given x, and our B hat is the best linear unbiased linear estimator. Simple stuff, guys. I don't want to spend too much time here, but basically it's a reinterpretation of what we did in a statistical setting. And I don't know, I think not many of you guys have taken statistics, like estimation theory yet. So usually it's a master course. So you're going to receive this interpretation later on when you take some master courses on statistics. I know that unfortunately, they prefer to focus more on electronics and chip design and statistics. So I assume some of you are not too familiar with this statistical estimation techniques. So I'll wait for you to see them in some other classes later on. Okay, very good. So this time I try not to go long. I know the class finishes at 10. Okay, so we talk next time, guys, with the me challenge report. Try to do as much as possible. Try to at least give me like a solid challenge 1 to 5, and then sorry, task 1 to 3, let's say, and then I'll let you finish in 2 weeks. Okay, I'm gonna stop the recording now. We say hi to the people of YouTube. Ciao, 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 ciao. Remember to subscribe and click like and whatever. Okay, ciao.